Hello. Today we'll be discussing how to add tree models from the book Practical Statistics for Data Scientists by Peter and Andrew Bruce. Before we begin, I want to define a few key terms that will be used throughout the tutorial. Recursive partitioning is when you repeatedly divide and subdivide your data with the goal of making the outcomes in each final subdivision as similar as possible. Split value is a predictor value that divides the records into those where the predictor is less than the split value and those where it is more. A node is a graphical or rule representation of a split value in a decision tree or in a set of corresponding branching rules. A leaf is the end of a set of if-then rules or branches of a tree. The rules that bring you that leaf provides one of the classification rules for any record in a tree. An impurity is the extent to which a mix of classes is found in a subpartition of the data. The loss is a number of misclassifications at a stage in the splitting process. The more losses, the more impurity. Pruning is the process of taking a fully grown tree and progressively cutting its branches back to reduce overfitting. Tree models, also called classification and regression trees, are an effective and popular classification and regression method that was developed in 1984. Tree models and their more powerful descendants, random forests and boosting, form the basis for the most widely used and powerful predictive modeling tools in the data science for regression and classification. A tree model is a set of if-then-else rules that are easy to understand and to implement. In contrast to regression and logistic regression, trees have the ability to discover hidden patterns corresponding to complex interactions in the data. However, simple tree models can be expressed in terms of predictor relationships that are easily interpretable. As mentioned earlier, this tutorial is following the examples used in the book Practical Statistics for Data Scientists by Peter and Andrew Bruce. I will attach a link to the dataset used in the description below if you would like to follow along. Before we start, in your R setup chunk, install the readr, rpart, dplyr, and ggplot2 libraries. Then you'll want to read in your CSV file and assign it to a variable. The two main packages to fit tree models into R are rpart and tree. Using the rpart package, a model is fit to a sample of 3,000 records of the loan data using variables payment inc ratio and borrower score. For this example, we will display a text tree. First, we need to create an outcome variable that pulls from the loan table. Then we will create the loan tree variable using the rpart command. In this example, we are using CP, which stands for complexity parameter. Any split that does not decrease the overall lack of fit by a factor of CP is not attempted. Then we call the loan tree variable to display the text tree. The depth of the tree is shown by the indent. Each node corresponds to a temporary classification determined by the dominant outcome in that partition. The loss is the number of misclassifications yielded by the temporary classification in a partition. For example, in node 2, there were 474 misclassifications of 1,496 total records. The values in the parentheses correspond to the proportion of records that are paid off and default, respectively. For example, in node 13, which predicts default, over 60% of the records are loans that are in default. These classification rules are determined by navigating through a tiered tree, starting at the root and moving left if the node is true and right if not, until a leaf is reached. Typically, the tree is plotted upside down, so the root is at the top and the leaves are at the bottom. For example, if we get a loan with a borrower score of 0.6 and a payment inc ratio of 8.0, we end up at the leftmost leaf and predict that the loan will be paid off. For this next example, we will go over displaying the tree. Using the plot command, call the loan tree, set uniform to true and make the spacing even, and use margin to set the width of the diagram. Then use the text command to display the text on the tree. The algorithm to construct a decision tree, called recursive partitioning, is straightforward and intuitive. The data is repeatedly partitioned using predictor values that do the best job of separating the data into relatively similar partitions. For a partition A of records, recursive partitioning will find the best way to partition A into two subpartitions. The recursive algorithm has 4 parts. First, initialize A with the entire dataset. Second, apply the partitioning algorithm to split A into two subpartitions A1 and A2. Third, repeat step 2 on subpartitions A1 and A2. Fourth, the algorithm terminates when no further partition can be made that sufficiently improves the uniformity of the partitions. The end result is a partitioning of the data. In addition to a binary prediction, tree models can produce a probability estimate based on the number of zeros and ones in the partition. The estimate is simply the sum of the zeros and ones in the partition divided by the number of observations in the partition. For this second example, I have already typed out the equation, so all we have to do is create the ggplot. First, we will call the loan data and plot the borrower score and payment ink ratio. Then we will plot the outcome by color, make the plot size a bit larger, and make larger numbers less transparent. We will then use the scale color manual method to change the plot colors to black and red to make it a bit more readable. Using the geom segment, we will add the rule number lines 1 through 5. To change the size of the key, we will use the guide method. I use the scale x and y continuous methods to set max limits on the x and y axis to focus the majority of the data displayed. The final 2 commands add labels to the table based on the decision column of our dataset, then removes the shading from the key. Tree models recursively create partitions A that predict an outcome of y equals 0 or y equals 1. You can see from the preceding algorithm that we need a way to measure consistency, also called class purity, within a partition. Or, equivalently, we need to measure the impurity of a partition. The accuracy of the predictions is the proportion P of misclassified records within that partition, which ranges from a perfect score of 0 to a purely random guessing score of 0.5. It turns out that accuracy is not a good measure for impurity. Instead, 2 common measures for impurity are the Gini impurity and entropy of information. While these and other impurity measures apply to classification problems with more than 2 classes, we focus on the binary case. The Gini impurity for a set of records A is IA equals P times 1 minus P, whereas the entropy measure is given by IA equals negative P times the P of log 2 minus 1 minus P times 1 minus P of log 2. For example 3, we will go over how to graph the Gini impurity and entropy measure. First, we will set the variable x to 0, 50, divided by 100. Then we will create the algorithm for the Gini impurity, which I have commented in the code block. Below that, we will create the algorithm for the entropy measure, which I have also commented within the code block. Then we will create a variable impure and set it to a data frame to find the points to be displayed in the ggplot. To create the plot, we will use the data from the impure variable to graph x and impurity. The lines and colors will be determined by the type variable. Then we will make the lines thicker by setting the size. Similar to the last example, we are adding the guides method to change the key width and using the scale x and y continuous to focus in on the data. We are also using the theme BW to remove the key shading and the theme method to remove the key title. The impurity metric is used in the splitting algorithm described earlier. For each proposed partition of the data, the impurity is measured for each of the partitions at each stage, where the lowest weighted average is selected. As the tree grows bigger, the splitting rules become more detailed, and the tree gradually shifts from identifying big rules that identify real and reliable relationships in the data to tiny rules that reflect only noise. A fully grown tree results in completely pure leaves and hence 100% accuracy in classifying the data that it is trained on. This accuracy is, of course, misleading. We overfit the data, fitting the noise in the training data, not the signal that we want to identify in the new data. The first way we can stop a tree from growing is by using minsplit and minbucket. We can avoid splitting a partition if a resulting subpartition is too small, or if a terminal leaf is too small. In our part, these constraints are controlled separately by the parameters minsplit and minbucket, respectively with defaults 20 and 7. In this example, we will set the variable minsplit to 1500. Then we will display the original text tree. Minsplit is the minimum number of observations that must exist in a node in order for a split to be attempted. Then we will display the text tree using the minsplit. Minbucket is the minimum number of observations in any terminal leaf node. If only one minbucket or minsplit is specified, the code either sets minsplit to minbucket times 3 or minbucket to minsplit divided by 3 as appropriate. The last step then is to display the third tree. The second way we can stop a tree from growing is using the complexity parameter, abbreviated as CP. However, don't split a partition if the new partition does not significantly reduce the impurity. In our part, this is controlled by the CP, which is a measure of how complex a tree is. The more complex, the greater the value of the CP. In practice, CP is used to limit tree growth by attaching a penalty to additional complexity splits in a tree. The most common way to estimate a good value of CP is via cross-validation. First, partition the data into training and validation sets. Second, grow the tree with the training data. Third, prune it successfully step by step, recording CP at each step. Fourth, note the CP that corresponds to the minimum error on the validation data. Fifth, repartition the data into training and validation, and repeat the growing, pruning, and CP recording process. 6. Do this again and again and average the CPs that reflect minimum error for each tree. Finally, go back to the original data, or feature data, and grow a tree, stopping at this optimum CP value. In our part, you can use the argument CP_table to produce a table of the CP values and their associated cross-validation error, or X error in R. To do this, collect the data from lone tree and set digits to get option digits -2. Predicting a continuous value, also termed regression, with a tree follows the same logic and procedure, except that impurity is measured by a squared deviation from the mean squared errors in each subpartition, and predictive performance is judged by the square root of the mean squared error in each partition. One of the big obstacles faced by predictive modelers in organizations is the perceived black box nature of the methods they use, which gives rise to the opposition from other elements of the organization. In this regard, the tree model has two appealing aspects. First, tree models provide a visual tool for exploring the data to gain an idea of what variables are important and how they relate to one another. Trees can capture nonlinear relationships among predictor variables. Second, tree models provide a set of rules that can be effectively communicated to non-specialists, either for implementation or to sell a data mining project. When it comes to prediction, however, connecting the results from multiple trees is typically more powerful than just using a single tree. In particular, the random forest and boosted tree algorithm almost always provides a higher predictive accuracy and performance, but the advantages mentioned above of a single tree are lost. This concludes our demo on tree models from the book Practical Statistics for Data Scientists by Peter and Andrew Bruce.